Hi, my name is Brian Muncie. I'm Western Regional Sales Manager with House of Batteries in Southern California. Over the last 25 years or so, I've been involved in the design, engineering, selection and sourcing of components, assembly and quality control for battery pack assemblies in every chemistry for many different electronic applications. In this brief presentation, I'll be sharing a little bit of what I've learned over the years with you about lithium-ion and polymer chemistry in particular. Here's a brief overview of the presentation. First, we'll begin with a bit of background information, some history, and talk about the strengths and weaknesses of rechargeable lithium technology in general. Then we'll move on to specific lithium cell types and talk about different cathode and anodes that can be used to yield different performance characteristics. Then we'll talk a bit about safety circuits, which might be the most important aspect of lithium-ion and polymer battery pack assembly and design. We'll talk some about charging and how through different charging regimes you can increase the calendar or cycle life of a lithium battery. Then we'll talk about storage, which is an often overlooked aspect of lithium-ion technology. We'll talk a bit about packaging and shipping, which is a very important aspect also, since there are many regulations surrounding the transport of lithium batteries. Then finally, we'll talk a bit about qualifying assemblers, because not any small garage shop can safely and reliably design and assemble lithium-ion and polymer batteries. Because lithium is the lightest metal and has the most electrical potential, scientists and engineers worked long and hard during the 20th century to try to introduce lithium rechargeable batteries into the marketplace. It wasn't until around 1991, though, that Sony was finally able to introduce a safe and reliable product. They produced an 18650 size cell, 18 millimeter by 65 millimeter, that was about a 1.2 amp hour cell and 3.6 volts. Since the introduction of that product in the early 90s, the technology has continued to mature and has become the dominant technology for portable electronics. Lithium-ion and polymer cells are a large family of cells that use different anode and cathodes to produce different performance characteristics such as high energy or high power characteristics, and we'll talk about some of the specific technologies in future slides. Most lithium cells are rated at about 3.6 or 3.7 volts, although some technologies like lithium iron phosphate are only 3.3 volts per cell, and lithium titanate are around 2.4 volts per cell. Again, the cells can be engineered for specific performance advantages such as high power, high energy, long calendar life, etc. And after 25 years or so in the commercial market, lithium-ion cells are the dominant technology for portable electronics, and we'll talk a little bit about why that is the case. This chart is a graphic illustration of why lithium-ion and polymer cells and batteries are such a popular choice for today's electronic applications. As you can see toward the left of the chart, in 1991, when the technology was first introduced into the market, the cost was quite high and the energy density was marginal. In the last 25 years or so, you can see that the energy has steadily risen as technology has improved and the cost has been reduced dramatically. And so again, this is one of the big reasons why lithium is so popular today. This chart illustrates the narrow band of voltage and temperature that lithium-ion cells and batteries can safely operate. To operate in the safe green zone on this chart requires a carefully designed and tested electronic circuit that is attached to the cells of the battery pack. This is called a battery management system, or BMS for short, and we'll be talking in more detail about these circuits in later slides. Here are a few of the reasons why lithium-ion and polymer cells are so popular in today's electronic applications. They have high energy density, especially compared to some of the other older, more established chemistries, and we'll show that graphically in a chart in an upcoming slide. They're under continual development. For example, over the last 20 to 25 years, the capacity of the 18650 cell has grown by quite a bit. When Sony introduced the first 18650 cell in 1991, it was rated at about 1.2 amp hour. The cells that are shipping today in the 18650 size are about 3.4 to 3.6 amp hour, and further capacity improvements are not far away. They do not need any prolonged priming or cycling. The first charge on a lithium battery will yield 100% of its rated runtime. They have a relatively low self-discharge rate, although there are some special provisions for storing lithium-ion cells and batteries, which we'll talk about in a later slide. There is no special maintenance regime needed for lithium cells and batteries. No memory effect, although some recent studies have shown that there might be some type of a memory effect that can take place in lithium iron phosphate cells and batteries. They're environmentally friendly, free of any heavy metals, although they are still subject to recycling. And specialty cells can and have been developed to provide performance characteristics such as very high current rates or low and high temperature characteristics. We'll talk a little bit about some specialty cells in future slides as well. As popular as lithium-ion and polymer cells and batteries are in today's electronic applications due to the number of advantages they offer, they do also have a number of limitations, which can sometimes make them not the best choice for an electronic application. A few of the limitations are the following. They do require protection circuitry, which adds to the complexity of the battery assembly and to the development time as well. They can be subject to aging when stored, and a chart that we'll have in a later slide will illustrate that graphically. They can be perceived to be not as safe as other chemistries due to some well-publicized incidences. However, the number of lithium battery failures in consumer electronics and commercial applications is extremely low. They actually have a very, very good track record. The transportation regulations require that the cells and batteries be tested and specially packaged for shipping, which adds to the cost and complexity of dealing with lithium batteries. They can be more expensive to manufacture than other chemistries due to the added electronics and, again, some of the regulatory requirements that surround the shipping of the batteries. Also a fast-moving technology. Cell sizes tend to come and go, especially in the polymer, so end of life can be a real issue if you have an application that you want to keep in the field for perhaps 5 or 10 years or more. Next, we'll talk about the different cell types. Most of the different lithium cell types are based on a change or a difference in cathode materials, although the lithium titanate is a different anode material. And while we're talking about the different cells, we'll learn about the developments that have taken place in the different technologies over the last couple of decades, such as capacity improvements, the lowering of cost, some special high drain cells, and some of the cells that are also said to be safer as well. Lithium cobalt oxide batteries were the original lithium-ion cell introduced by Sony in 1991. When they were introduced at that time, they used a coke anode, but soon thereafter switched to a graphite anode to achieve a flatter discharge curve. Lithium cobalt oxide does have very good energy density, but relatively limited drain rate capability compared to other newer lithium chemistries. Because they're the most established chemistry in the lithium-ion family, they are made by quite a few Chinese manufacturers inexpensively today. So because of that, the high energy density and the low cost relative to some of the other lithium chemistries, they are a popular choice for cell phones, laptops, and cameras. Lithium manganese oxide or spinel cells were developed later in the 1990s as an alternative to the lithium cobalt oxide and its perceived deficiencies, particularly in the area of discharge rate capability. Because the manganese oxide cathode yields a cell with lower impedance, the manganese or spinel cells have a better fast charge capability and better high rate discharge capability than the lithium cobalt oxide cells. The downside is that they do have lower capacity, but even so, they still have better energy density than some of the older nickel-based chemistries. Applications for the manganese cells are power tools, electric vehicles, and some medical and hobby applications. Although newer technologies such as the lithium iron phosphate have taken the place of the manganese cells in more recent years. After the development of lithium cobalt oxide and lithium manganese oxide cells in the 1990s, engineers turn next to blending different materials with the cobalt in the cathode to achieve different results. By reducing the amount of cobalt in the cathode, they are able to reduce the manufacturing cost because cobalt is an expensive material. And by using different amounts of nickel or manganese, nickel and aluminum or other materials, they can achieve different specific characteristics such as high rate discharge capability or high energy density or runtime. The nickel manganese cobalt is one such variation. It is charged at a lower peak voltage than some of the other lithium chemistries. Cobalt oxide and manganese oxide cells, for instance, are charged to a peak of 4.2 volts, whereas nickel manganese cobalt is charged to only 4.1 volt to achieve a long cycle life. They are safer than nickel cobalt oxide cells, less prone to thermal runaway. They can be tailored for high power applications, but they can also have lower capacity depending on the particular blend in the cathode. Applications can be power tools. They're a popular, nickel manganese cobalt is a popular cathode in electric vehicle applications, and there are some uses in the medical and hobby industries as well. The nickel cobalt aluminum cathode is another example of a metal blended cathode material that has been used with great success. It achieves the highest energy density in 18650 cells that are commercially available, and it's an example of how far the technology has come. When Sony first introduced the 18650 cell in 1991, it was rated at about 1.2 amp hour in a cobalt oxide cathode material. Today, with the nickel cobalt aluminum cathode, cells are shipping with 3.4 amp hour or even more capacity when combined with a silicon anode. Despite the higher cost of this cell, many consumers are willing to pay more for the energy density that it provides. Lithium iron phosphate is a chemistry that has become much more popular in the last 10 years or so. This is for several reasons. Lithium iron phosphate cells have long cycle life, good calendar life, and 4 cells in series yield 12.8 volts, which is a nice drop-in replacement for lead-acid batteries. One of the disadvantages, however, to lithium iron phosphate is it does have lower cell voltage than other cathode materials and therefore has lower energy density. Nonetheless, it is said to be a safer battery chemistry and less prone to thermal runaway, although they still do require battery pack protection circuitry. Lithium titanate cells are different in that they change the anode material rather than the cathode material, as we've been talking about in previous slides. The graphite anode is changed out for a titanate anode and leads to some interesting and good characteristics for certain applications. These cells have extremely low impedance and therefore are able to take a very rapid charge and discharge rapidly as well. They also have good low temperature performance and are said to have better cycle life than other lithium chemistries. They do, however, have lower cell voltage of only 2.4 volts per cell and have mostly found their way into electric vehicle applications and not so much into portable electronics. Lithium polymer cells are really lithium-ion cells with a different style packaging. They use the same cathode materials as the other lithium-ion cells that we've talked about so far. Most are lithium cobalt oxide, but the big difference in a polymer cell is that it's in a soft foil aluminum style pouch rather than a hard steel or aluminum can. And so this offers a lot of different options in terms of cell sizes and makes it less expensive to tool up a new cell as well. One of the disadvantages, though, is that cell sizes do come and go quite a lot and that there are no industry standards that you can look at from one manufacturer to the next. However, lithium polymer cells are very popular in today's electronic applications because of their thin form factors, perhaps as few as 2 or 3 millimeters thick in some cases. Here's a nice chart that shows a comparison of all the different chemistries that we've been talking about and then also adds the older more traditional lead acid and nickel-based chemistries as a comparison. You can see that the traditional lithium cobalt oxide cells toward the right side of the graph have very good energy density, only recently surpassed by the nickel cobalt aluminum. The lithium iron phosphate and manganese cells do have lower energy density but do have better power capabilities, are less prone to thermal runaway, and also have better cycle life. This is a slide that we looked at earlier, but we'll look at it one more time as an introduction to the safety circuits that are such an integral part of the safe and reliable operation of lithium-ion cells and batteries. It's a reminder that lithium-ion cells can only operate safely within a pretty narrow range of voltage and temperature. Otherwise, they can experience safety issues, thermal runaway, what's called in the industry as rapid disassembly, or venting with flame. So with that, we'll move on to the details of what are needed, the features that are part of the safety circuit design and implementation. If the cells are the heart of a lithium battery assembly, then the safety circuit, the BMS, short for battery management system, is the brains of the battery assembly, and probably the most important part of making sure that lithium battery operates safely and reliably in an application. So we'll go over a few of the most important features of safety circuit design. The first is overcharge protection in case the charger fails to terminate at the proper peak voltage, which is about 4.2 volts for most lithium chemistries, but as low as 3.6 for lithium iron phosphate. If the charger fails to terminate properly at that peak voltage, then the safety circuit will kick in at perhaps about 4.3 volts or so for most cell chemistries. Over discharge protection is equally as important, because if lithium-ion cells are over discharged or discharged to a very low voltage, then they do become permanently damaged and unsafe for use. Typically, cutoff voltage is 2.5 volts or maybe 2.7 volts per cell. But it's very important not to rely on the safety circuit as the primary method of disconnecting the load from the application. The application should itself shut down well above the 2.5 or 2.7 volt per cell threshold, perhaps at 3 volts per cell or something close. Overcurrent protection is another feature of safety circuits to protect against short circuits and overcurrent events, and is a resettable feature so that it doesn't permanently disable the battery pack. And then temperature sensing is a good feature to have on lithium-ion batteries as well, so that you can monitor the battery pack for an unusual or unsafe rapid rise in temperature, either caused by the charger not terminating properly or some other event. Redundancy is also a good idea, perhaps adding passive fuses or temperature cutoff devices in addition to the safety circuit adds another layer of safety to the battery pack. The safety circuit electronics that are installed in lithium battery assemblies also afford the opportunity for additional functionality or additional options. One of the more popular options on lithium batteries is the addition of a fuel gauge that lets you know how much runtime is remaining on the battery pack. And older fuel gauges used voltage-based methods or Coulomb counting. Newer fuel gauges use topologies like impedance tracking, which is a much more accurate way of determining the state of charge of the battery. Cell balancing is another option, is almost actually necessary for any more than 2 or 3 cells in series, or if you're using lithium iron phosphate, it's definitely a must. 2 ways of cell balancing are passive through the use of resistors, which is a less expensive method but generates heat, which can age the cells prematurely. Active cell balancing does cost more but doesn't generate the heat that the resistors do in a passive system. Communication with the host device goes hand in hand with the fuel gauge, and different protocols for that are the SM bus battery protocol. I2C is another popular communication method, and CAN bus has also been widely used, adopted from the automotive industry, and is widely used, of course, in electric vehicle applications. Another option that can be put onto the BMS or battery management system is charge control, which eliminates the need for a smart charger. Since all of the functionality is built right into the battery pack, you can use a little wall wart power supply or a desktop power supply to charge the battery. But care must be taken when designing charge control into lithium battery packs, because the charge circuitry does generate heat, and if some cells are closer to the charge circuit than others, they could age at a faster rate, being exposed to the heat that's produced by the charge control circuit. So careful design and isolation of the cells is necessary when incorporating that function into a BMS on your lithium battery pack. Battery packaging is also a very important consideration when designing and assembling a lithium-ion battery pack. A soft shrink wrap battery pack is okay if the battery will be more or less permanently installed into the device and will not be regularly handled by an end user. Only a technician might replace the battery infrequently. If a user is expected to handle the battery regularly or change it out on their own, then the battery has to be protected in some kind of a hard shell enclosure, plastic, metal, or other material. This is because if the battery is dropped or there's an impact event, the BMS or protection circuitry could be damaged, but it might not be evident immediately. And the battery might appear to function properly and only later on would have a malfunction that could cause a safety problem. So packaging is a very important consideration also when designing and assembling lithium-ion batteries. Another important consideration in lithium battery design is the type of application you'll be putting the battery into. The two broad categories are cyclic applications and standby applications. Most applications for lithium batteries are some form of a cyclic application. In other words, an application where the battery is used daily to some degree and then charged every day or every night. In applications like this, it's important to consider how many cycles are needed over the long haul and how much runtime will be needed. And it's important to design in reserve capacity. The more capacity that you take out of the battery each cycle, the less the calendar life will be on the battery pack. So it's important to build in extra capacity if you can into the design. Standby applications are applications where the battery is sitting stationary and unused for extended periods of time, but is required to supply power immediately on demand if there is an event that calls for the power to be drawn. Applications such as uninterruptible power supply systems and telecommunications systems use batteries in standby applications. Again, it's important to consider what the calendar life will be on the battery and to select a cell chemistry that is a friendlier type for a standby application, such as perhaps a lithium iron phosphate cell. Also, you can extend the calendar life of the battery by charging the batteries at a lower voltage, and we'll talk more about that in an upcoming slide. Again, very important to build in reserve capacity for both cyclic and standby applications, because what you want to determine is at some point down the road, either months or years down the line, you want to have a certain amount of runtime available. So you want to make sure that as the capacity of the battery pack fades over time, you still have enough capacity or runtime at the end of the calendar life of the battery to supply as much runtime as you will be needing. Charging of lithium-ion cells and batteries is a pretty straightforward affair. There's a algorithm that starts with a constant current charge, and then once the cell or battery reaches a set peak voltage, it converts over to constant voltage and does a slow taper off of current until the charge finally terminates altogether. There are a couple of ways to increase the life, both the cycle life and calendar life of a lithium-ion battery. One way is to lower the peak voltage. This graph or chart is typical for a lithium cobalt oxide cell. But one way to increase the life of the cell or the battery would be to lower the max voltage from 4.2 to 4.1 volts. And also you could lower the current that goes into the charge during the first constant current state of the charge. And another thing you can do to increase the cycle life or calendar life is to skip the constant voltage or saturation charge altogether. And that what will happen is the constant current portion of the charge will get the battery about 80% charged, and then if you terminate it right there, it will definitely increase the cycle life and or calendar life of the cell or battery if you can live with an 80% runtime on every cycle. So a couple of things to think about there, some options for charging and ways of increasing the cell or battery life. This chart is an illustration of the points we were talking about in the last slide about charging options, and that the lower voltages will yield lower capacities. This also shows you the charge time in minutes and what you might expect to get for a runtime if you're charging at lower voltages. Again, keeping in mind that the lower capacity and lower voltage charge will yield results in more cycles or longer calendar life. And again, another option is to remove the battery from the charge prior to the saturation phase of the charge, which generally will end up at about 80% state of charge if you're charging to the peak voltage. And that will also increase the cycle life or calendar life of the battery as well. An often overlooked aspect of lithium-ion and polymer cells and batteries, and one that is not talked about very much by manufacturers, is storage. Cells are shipped from the cell manufacturer at about a 30 to 50% state of charge. This is because they actually store better that way. The chart on this slide shows what will happen if the battery's topped off and stored at 100% state of charge. You actually end up losing more capacity permanently than if the battery is stored at a partial state of charge. So this is an important consideration if you know the batteries will be sitting inactive for a long period of time. Another important consideration with storing all batteries of any chemistry is the temperature. The higher the temperature, the more rapidly the battery will lose its charge and also deteriorate. Batteries are like most other physical devices. The harder they are worked, the faster they will wear out. So again, it's important to over-spec the battery if you can. Don't push it toward the edge of its envelope when you're using it. The faster you charge it, the faster you discharge it, even though the cell specification may say it's capable of performing at that rate. The harder you work the battery, the faster you will wear it out. So try to build some headroom into the design of the battery pack. Don't push it to the limit of its capabilities, otherwise you'll be compromising the cycle life and or the calendar life. Another important aspect of working with lithium batteries and deciding whether or not a lithium battery is the best one for your application are the shipping regulations, which add to the cost and complexity of dealing with lithium batteries in a manufacturing environment. Because of the potential safety problems that lithium batteries could pose during transport, there are some international regulations that need to be complied with in terms of testing the lithium batteries and shipping them in the proper and compliant packaging. Here is a brief description of the tests that are required for lithium batteries to be compliant with international shipping regulations. A small quantity of lithium batteries prototypes can be shipped for testing purposes only prior to having these tests completed, but once you go into production, these tests definitely need to have been successfully passed. The tests are known in the industry jargon as T1 through T8 and are designed to simulate what the battery might see during air transport. The two toughest tests seem to be the vibration and the shock test, and so careful design is necessary to ensure that the battery can stand up to the abuse that it might see during transport. Here are the general requirements for submitting batteries to a laboratory for tests T1 through T8 that were discussed on the previous slide. 16 rechargeable batteries are submitted to the lab for testing, and 8 of those batteries need to be cycled 50 times prior to testing. This can be done at the battery assembly facility, or the laboratory can do this function as well for an extra fee. Lead time for testing is typically around 6 weeks, and cost can be $5,000 to $10,000. So this is definitely something that needs to be considered when you're designing a lithium battery into your application so that you can plan accordingly for cost and lead time. Another aspect of shipping lithium-ion batteries is making sure that the packaging, labeling, and documentation is all correct and compliant with current regulations. The boxes must be of an approved type, the labels must be the proper labels, and the documentation must be filled out correctly. The shippers must be trained and certified in shipping hazardous materials. After reviewing the different cell technologies and electronics used in lithium battery assemblies with an emphasis on safety, here are a few points, reminders of what's at stake if cheaply or inexpensively built batteries are used. The cost that you save up front might be more than offset by failures in the field that could necessitate recalls or perhaps even worse. Substandard or counterfeit components can cause any number of problems. When dealing with cell manufacturers, you definitely want to make sure, if it's not a Tier 1 manufacturer such as Panasonic or Samsung or another name like that, that you do a factory inspection to make sure that they have the systems and procedures in place and the equipment capable of manufacturing a quality and consistent and safe cell. With regards to the electronics, you definitely want to make sure that no counterfeit components are making their way into your circuits, and that the circuit is safe and reliable in mass production quantities, because the consequences, as I say, could be quite expensive if there are failures, or even worse if there was some sort of injury or property damage. Here's an example of what can happen to a lithium battery when things go wrong. You definitely don't want this happening with any battery pack that you've designed or are manufacturing. To avoid an event like this in the field, it's very important to make sure that you've used the best cells possible, and also to make sure that the safety circuit has been well designed and thoroughly tested, and that it avoids the use of substandard or counterfeit components. Also, you want to make sure that the packaging is robust enough to protect the battery components inside to avoid any damage, so that failures like this don't occur in the field. Lastly, here is a checklist for qualifying assemblers that you'll partner with on your lithium-ion battery pack assembly. What are their engineering resources? Do they have a large staff of electrical and mechanical engineers who are experienced in the design and manufacture of lithium-ion battery packs? What kind of quality systems do they have? Have they been audited and approved by medical manufacturers, defense contractors, aerospace manufacturers, and large quality-oriented clients? What kind of equipment do they have? Do they have a lot of test equipment that they can use to validate designs and systems? Are they an authorized assembler for the big names in the industry? Are they a certified hazmat shipper? Do they have experience and are shipping properly compliant to regulations? And do they have references? Who are their clients? Are they well respected in the industry? Just a few things to think about when qualifying a battery pack assembler. If you are a manufacturer of an electronic device that requires a battery in any chemistry for any application, we would welcome the opportunity to assist you with your design and assembly. Please feel free to contact us through our website or by phone. Thank you.